Welcome to the class. We have been discussing digital modulation techniques for a few classes now. We actually started digital modulation in the last class. Previous to that, we discussed about baseband representation of band pass signals in the first two classes in this module. And in that context, we have discussed low pass equivalent signal of a band pass signal, and we have seen how to that we can convert a band pass signal into low pass signal. That signal we call low pass equivalent signal, and it doesn't lose any information. And we can convert the low pass equivalent signal back into pass band signal. So this conversion from band pass to low pass is called the down conversion, because the frequency comes down, and the conversion from the band pass from the low pass equivalent signal to the equivalent band pass signal is called the up conversion. And we have seen that this conversion takes has certain properties, nice properties. For example, if we take also the low pass equivalent system of a band pass system, and that system fully characterizes the original system. So, and then we have discussed one modulation technique called pulse amplitude modulation. That is one digital modulation technique we have discussed so far. And we have seen that pulse amplitude modulation is basically just modulating one single pulse depending on the symbol that is to be transmitted. So if it is binary pulse amplitude modulation, that is 2 PAM, then we have a pulse GT or PT, then we scale that, that is to change the amplitude depending on what we want to transmit. If we want to transmit 1, we will transmit 1 amplitude. If we want to transmit 0, we transmit another amplitude of the same pulse. So now this pulse PT may be a baseband pulse, just like a rectangular pulse, in which case the spectrum of the resulting transmitted signal will be a low pass signal, or it may be a passband pulse, meaning by it may be a shape but it is modulated by sinusoid. Then the spectrum of that pulse itself is not low pass, it is band pass. It will have center frequency, that Fc, which is the frequency of that sinusoid. So we have seen that if we, for example, if we take this pulse for baseband PM, we get one spectrum like this. But if we take a passband pulse, band pass pulse, it is not this, but it is modulated by this. So like this, then the spectrum will be centered at Fc. So it will be like this. So if you want to do passband modulation, we just need to modulate the pulse by a sinusoid. So if we use such a modulated pulse as the carrier for our pulse amplitude modulation, then we will have a passband spectrum, band pass spectrum of the resulting transmitted signal. So that is called passband PAM. Now instead of binary, we have seen that we can have different M-ADI modulation scheme, where M equal to 2 power B. So if you want to transmit B number of bits per symbol, then those 2 power B possible values will be mapped first to some real numbers, some amplitude levels, like 1, 2, 3, then -1, -2, -3, several amplitudes we can map, and then take those amplitudes of the PAM pulse. So that will be multiplied by to the pulse PT, and then that will be transmitted. So that will be done in every symbol. So we have seen such examples, and we have also seen in the last class how to demodulate a simple binary PAM signal, or binary, or in fact any PAM signal when the pulse is a rectangular baseband rectangular pulse. So, if we have this PT rectangle T1, then we have seen in the last class, then the best thing to do no, not the best thing, but we have not seen that, but we have seen that one way to modulate demodulate this is to integrate the received signal. So, received signal, if we transmit one, so we will have two levels for 1, 0, or if you have m at PAM, then we will have many more levels, m number of levels. So, for 4 PAM, for example, we can have -1, -3, -1, 1, 3. So, we can have different levels, -1, 3, 1, 3. We can have these 4 levels, and then we can multiply those numbers to this and transmit depending on what you want to transmit. If we want to transmit 0, 0, we will probably take this 0, 1 to this, 1, 0 to this, and 1, 1 to this. So, if you want to transmit 0, 1, we will transmit minus PT. So, now whatever we transmit, it will be ultimately corrupted by noise. So, what we will receive if we, for example, transmit -1, 0, 1, we will have transmitted this in 0 to t, but we would receive something like this, some corrupted by noise. So, now the way to one way to demodulate is integrate this pulse in this interval. So, take 0 to t and then integrate this value, and then if that is so that value we can compare with, suppose if it is -1, it would give some value, if it is -3, it will give some value, if it is 1, it will give some value, and so on for 3. So, we will integrate and then see to which of those values it is nearest. So, that we will pick. So, if we integrate, we will see that it is nearest to, it will be somewhere here probably. Then we will pick -1 because it is nearest to -1. Okay. So, we have also seen that doing this operation, this operation can be done in terms of a filter and sampler. So, we can have a filter with impulse response PT, which is same as PT minus capital T minus T in this case. So, we will take RT will be passed through this and then sampled at T. Then we will get the same output as the integration of this here. We can write here PT, but impulse response as PT, but we will see that for other pulse shapes, it is not actually PT. In this case, we should have P capital T minus T. So, for other pulse shapes, it will matter. For this particular pulse shape, rectangular pulse shape, the both PT and P capital T minus T are same. So, it does not matter what you call it. But for other pulse shapes, it will matter. That we will see later. So, we will now investigate a generalization of this. We will see. So, in this case, we have seen that we should take HT, at least this is one choice, HT equal to P capital T minus T, pass it through this filter and then sample it. So, first pass it through this filter and then sample at T. This is one choice. Now, we will get an estimate of AK. If there is no noise, we will get exactly AK. If there is some noise, it will be added by some noise component. Okay. Now, we will consider a generalized situation. We will assume that we are using some arbitrary pulse PT and investigate how to demodulate the modulated signal. So, in this analysis, we will generalize the notations we have been using. We are assuming in this, when we are discussing PAM, all the examples we took have real valued pulse, but it need not be. If you are doing complex baseband case, equivalent complex baseband model, and you are first generating the complex baseband signal, and then from that we will do up conversion to transmit. So, to do that, we can have a complex pulse. So, we will assume that the pulse may be complex. We will assume that it is complex. If it is real, it is a special case. And then we will just draw the we will use some notations which I will introduce here. This is the block diagram of what is happening. We are transmitting here, this is xt. Then what we receive, this is the impulse response of the channel will be assumed to be Ct, and this received signal will be assumed to be Rt. And then we will pass through a filter. Here we have seen that we can pass through this filter and then sample at t. So we will take here one filter and sample, and we will see whether for arbitrary pulse shape this can be done, and if it can be done, what kind of filter we should take. So this is receive filter. This filter is called receiver filter or receive filter, and this signal what comes out of the receive filter is denoted by yt, and then we sample at every t second. So the samples will be y k times capital T. So at t equal to 1, k equal to 1, it will be sampled at t, it will be sampled at 2t for k equal to 2, and so on. So xt we know is the modulated signal. So xt looks like summation. So this channel also has actually noise. This is only the impulse response, but it has also noise. So here k equal to minus infinity to infinity, ak, and then p t minus kt. Okay. So now this will go through channel. So here what we will receive is Ct convolution this plus noise. So that convolution can be taken inside the summation, and then what we will get is p this pulse convolution Ct inside. So for convenience now on we will use the notation that Pt will be denoted by P1t. We will see why, because there will be several pulses we will consider. So this is P1t, and we have the channel. If we break this summation, you see that there are so many terms. Individual pulses are transmitted after delaying and scaling. So we will see what is happening to these individual pulses when it goes through all these systems. So it has impulse response Ct. There is actually noise here. So we will assume that this is the filter only, and we will add the noise outside. Then this goes to Rx filter, has impulse response At. Suppose we will see what At should be. This is now suppose I give only P1t as input to this, then what will come out here is also a kind of pulse. It is P1t convolution Ct. So that we will denote by P2t. And then here again it is P2t convolution At plus the noise convolution At. So this pulse we will assume that it is P3t plus some noise Nt convolution At. So if we denote it this way, so remember these things, this is the output only when you give this as input. Only one pulse you give as input. So P2t is nothing but P1t convolution Ct, and P3t is nothing but P2t convolution At. Then we are sampling at every t seconds. So if we transmit simply P1t, we will sample at capital T and see what we get. Okay. Now xt in terms of P1t, xt we have written as xt is summation k equal to minus infinity to infinity ak P1 t minus kt. Now, what we receive here RT is xt convolution Ct plus Nt. So, what do we receive when you give xt as input to the channel? We receive RT k equal to minus infinity to infinity. This whole thing convolution Ct, it is going through channel plus noise. So the convolution can be taken inside summation. So we can write Ak, then P1 convolution Ct plus Nt. Now, what is this term? We see that P1t convolution Ct is assumed to be P2t. So, if we shift this pulse by kt, the whole convolution result will be shifted. So, it will be P2 shifted by kt. So, we can have right here k equal to minus infinity to infinity Ak, then P2 shifted by kt plus Nt as it is. So what have we done here? We assume that P2t is convolution of P1t and Ct, that is P2t is the output when you give P1t as input to the channel, and similarly P3t is the output when you give P2t as input to the receive filter At. So that is P3t is convolution of P2t and At. Now the actual transmitted signal is this summation of so many pulses, shifted pulses after scaling. So when you do this convolution, what we receive here is this noise plus what we transmit here convolution Ct. So this whole thing convolution Ct, but that Ct convolution can be taken inside summation, and then that convolution, individual convolution, can be written as P2 shifted by kt. So we have here the noise plus this pulse P2t different shifted version. So it is like what we transmitted. What has happened? What we transmitted is this summation. What we have received is this summation. So what is the difference? Difference is that there is noise here. There was no noise here. So channel has added noise, and then the pulse was actually P1t that was transmitted. But here what we have received is P2t. So it is like, it is as if we have just transmitted using P2t, as if we did pulse amplitude modulation using a different pulse P2t. So we can assume that and see how to do demodulation. There is no need to consider channel, because ultimately what has come out is just like a PAM signal with a different pulse P2t and some noise is added. So now this signal goes through the receive filter. This signal goes through the receive filter. RT goes through the receive filter. So what happens then? We will see. So what we have here now is that Yt, which is the output of the receive filter, if RT is given as input, is now convolution of RT with AT. Now RT is now this whole thing. So RT will be convoluted to this summation and NT. So NT we can write NT convolution RT, and then here this summation convolution RT, but this convolution with RT can be taken inside summation again. Sorry, RT is this, so convolution with AT. So convolution with AT with noise, and then convolution with AT of this summation. So that convolution with AT can be taken inside, and then we have AK as it is, then P2 t minus kt convolution AT, that can be written as another pulse. And what is that? We have here Pt minus kt convolution AT. Now this whole thing, what is this? P2 shifted convolution AT. Now Pt without shifting, Pt convolution AT is assumed to be P3t, another pulse. So this will be, because this we have shifted P2 by kt, this this result itself will be shifted by kt. That is the result of convolution. If we shift one component by some time tau, then the result also will shift by tau. So, so here we can say this is now k equal to minus infinity to infinity a k p3t plus nt convolution at. So, what do we have? We have here, we have assumed the response of the channel to P1t to be P2t, and then Ct is the channel response, receive filter response, impulse response is At, then P2t can be written as Ct convolution P1t, P3t can be written as P2t convolution At, and then xt is, we know that it is PAM signal, so it is of this type, and then we have seen what we receive here, RT. RT is this convolution, and this we have brought to this form. This is P2 shifted. So it is like a PAM signal with this pulse plus some noise, and then after receive filter what we have got is again like a PAM signal. It is, this is P3t minus KT. So this is also like a PAM signal with again a different pulse P3t, then plus a noise which is not white noise now. So now what we are doing is we are sampling at multiples of time t. So we will sample at t, we will sample at 2t, and so on. So we will now see what we get if we sample. Now this whole thing we have assumed that it is, there is no assumption on this that P1t is real or anything. P1t can be complex, Ct can be complex, At can be complex, noise can be complex, everything is complex here. If it is real, it is a special case of this. Okay. So now we want to see what At should be. How should we actually design the receive filter? What is the criteria? So to do that, we will go into that, but before that we will actually assume something. We will assume that the receive filter is of something, and then analyze the case and then prove that that is the best thing to do. So we will do what is called, we will take what is called the matched filter. So At is matched to this pulse. So At is being convolved with this pulse, if you see here. So we will take At such that it is matched to P2 in some sense. So in this sense, we will take P2 star capital T minus T. So this is so here it is matched in some sense, you can see. Now what is this? If we will take an example, suppose P2T is like this. Here it is T, it is 0. If it is P2T, then what is this P2 star T minus? Star does not mean anything here because we have taken an example of real pulse. So P2 capital T minus T, star means nothing. So P2 capital T minus T is just flipped version of this. So it is the same thing even in this case, because this signal is, this pulse is symmetric. On the other hand, if we take this kind of pulse, P2T, this is At. If we take, for example, this kind of pulse, then At will be, it will be flipped. It will be flipped. So we see what it means to do this. Capital T minus T means basically flipping. 0 comes to T, T comes to 0. So this is called the matched filter. A filter with impulse response, this is called the matched filter to this pulse. A filter matched to the pulse P2T, that is the matched filter. Now we will take this particular filter as the receive filter and see what we get. Now remember that for rectangular pulse, rectangular baseband pulse, we actually took this filter. When we took example of a demodulation scheme, we actually took this filter and then sampled at the output. So in this case also, for general other pulse also, we are taking the same thing, and then we will see that we will be able to demodulate using this filter. So we use this filter, and then at the output of this filter we sample. So so to analyze what will happen, we will not assume that we are transmitting so many symbol after symbol. We will assume what happens to one symbol. Will we be able to demodulate if we transmit just one symbol? Then if we will see that if we can demodulate one symbol, we can demodulate the next symbol also. So we will take just one symbol and then see what happens. So suppose that we transmit just one symbol, so that xt is just one symbol, kth symbol. Suppose we transmit only the kth symbol. So it is transmitted between kt and k plus 1t. So p1 t minus k capital T. This is what we have transmitted. Then what will be the output? Yt. Output where? Output here. Output here, this Yt. So output Yt is so actually we don't output Yt is nothing but ak p1 t minus kt p3, because p1 will be convoluted with ct and then with at, so that will give us p3. This so what is a p3 we will see. So basically this is, so we will write in a different way. So y t is minus infinity to infinity. We are writing the convolution. So so at the receiver, before receiving filter, we will receive RT equal to AK P2 t minus KT plus NT. Then we pass it through the receipt filter AT. So we will get a convolution output as t minus say t minus tau, then r of tau d tau. This is the output. But we are sampling. So for demodulating the first symbol, that is the 0th symbol which does not have any shift, that we will sample at t and demodulate, and then see what is the best symbol, which symbol was transmitted. But for the kth symbol, we will sample at k plus 1 times t. So the output we have is k plus 1 times t. That is, from here we can see now that it is minus infinity to infinity, then a k plus 1 t minus tau, then ak p2 t minus kt, that is I am now writing r. So this is tau minus kt. We are evaluating at tau, so t will be replaced by tau, tau minus kt plus n tau d tau. So this is the sampled version. Yt is this, but we are sampling at k plus 1 t. So this is now ak minus infinity to infinity. Now a is, now you can see that we are taking the matched filter. So for matched filter we have this, at is p2 star capital T minus t. So we will replace by the at by that. So a of this whole thing will be put, this whole thing will be put in place of t. So here so we have p2 star then capital T minus this whole thing, capital T minus this whole thing will be tau minus k capital T, and then we take this part P2 tau minus kt. This is AK. There is another summation. This summation minus infinity to infinity P2 star tau minus kt n tau d tau. So, this part one can see is a noise, is the noise convoluted with this, and this thing, what is this thing? This is, you can see that this is the conjugate of this term. So, it is a real number which is the magnitude of this square. So, this is AK P2 tau minus kt square d tau. Now, what is this? There is no, actually if we do a change of variable in place of tau, if we put t plus kt, then this will be, this can be written as, AK minus infinity to infinity P2t square dt. So, this is basically the energy of P2t. So, this is E, the energy. So, this part is energy E of P2t times AK. Now, we have not written another term, that is noise. Here we have noise. So, this plus, we call it Nk. So, this plus Nk, this plus Nk. So, what have we done here? We have taken particularly a matched filter. We have taken this particular case. In the receiver filter is the matched filter, and then with that we have computed the output first, output of the receiver filter, that is Yt, that is convolution of the matched filter impulse response with the received signal, and that signal we have sampled at k plus 1 times t time. So, that sample value we have computed to be this. Now, what is this? What is this? This has two parts. One is E times AK. AK is the transmitted symbol value. AK is the transmitted symbol value, the level, the amplitude we have transmitted. We have multiplied to P2, P1t and then transmitted. So, that AK is the crucial part. If we know AK, we will know what is the bit stream we have transmitted in that symbol. So, if we are using 8 pm, then we would have transmitted 3 bits in that symbol. Then from AK we will come to know which 3 bits we have transmitted, whether it is 010 or it is 110, we will know if we know AK. So, now E is fixed, we can compute energy of P2t beforehand, because we will know the channel impulse response Ct, we will know P1t what we are using for PM, we will take the convolution and then that is our P2t. We can compute the energy of the P2t. So, E we know. So now we can divide this. So, y k plus 1 t we divide by E, that we will get as AK plus Nk by E. So, because E we know. So, we sample and then divide by E, then we get AK plus some noise. So, if the noise is small enough, we can estimate AK. This is an estimate of AK plus some noise. This is an estimate of AK, and the how good the estimate is depends on the noise value. If the noise is small, then we will be able to estimate AK fairly well. So, then from AK we will be able to recover the bits that we transmitted. So, this is the idea. So, we have seen in this few slides that by using a matched filter matched to the P2t, that is the output pulse of the channel, when you give P1t as the input. So, the output pulse is P2t. So, if we take the receiver filter as the matched filter of that pulse, that is matched to that pulse, then the output, if we sample at k plus 1t, then we get, and then we can divide, and then we get an estimate of ak, that is the level of the pulse that we transmitted. From that level, of course, we can again get the bits back. So, we have seen now this matched filter can be used to demodulate. Now, we will see whether matched filter is really the optimum. Can we use some other filter? So, we will see that, but before doing that, let us see some example of matched filter and what we receive at the output, etc. So example 1, suppose the channel is ideal, just delta t. The filter, there is no channel filter, just noise is being added at the channel. So, we will take that, this is a simple case, and we will take that case to see what is happening. So, and we take, let us say, P1t of this shape. Some level A. We take this pulse. Then what is P2t? P2t, if we remember, P is P1t convolution Ct. Now, Ct is delta t as assumed. So, this is nothing but P1t. Then what is the matched filter to Pt? It is At equal to P1 capital T minus T, where P1 is same as P2. So, what is, can we plot At? If we plot, it will be reversed. So, T will come to 0, 0 will go to T. So, this is T 0 A. This is our At. Now we actually pass Ak times this, as we assumed in the last analysis, that we transmit Ak times P1 this. So, let us say we are transmitting at the 0th symbol itself, not the kth symbol, k equal to 0 we are assuming. Then what are we transmitting? Ak times P1t. So, what will be the output of the received filter? If we forget the noise for time being, what will be the output? P3t is the output, Ak times P3t, but it is sufficient to analyze what is P3t. What is P3t? It is P2t convolution At. So, if we do this convolution, we will see that P3t is of this shape. T is here, 2t is here, it will be this shape. At T it is maximum. So, what we will receive at the output of the matched filter, this is matched filter At, and we will sample here at T, because we are transmitting from 0 to T, the 0th symbol, k equal to 0. So, here we have P2t plus noise, which we neglected, but we are transmitting, we are actually receiving this at the receiver. Then that we are passing through the matched filter. What will we get here? So it is actually A0 times P2t, the 0th symbol. Some scaling is also there. So what we will receive here is P2t convolution At evaluated at capital T times A0. So we will receive A0 P3 capital T. P3 is P2t convolution At plus NT convolution At, that we have to evaluate at T equal to capital T. So this is what we will receive. This is Yt, Y capital T here. Now what is this? Here we see that this A2, this is fine, this is At depends on this, but why are you sampling at capital T, that we want to see now. See, if we use this filter, why we are using this kind of matched filter we will see later, but suppose we use this filter, then we want to see why we are sampling at capital T. So if we use this filter, this noise is it capital T or it wherever, it will have the it will have the same variance. So, but here P3T is this. So, this P3T is maximum at capital T, you can see here. So, we want to amplify this A naught maximum, that is why we are sampling at capital T, because when you sample at capital T, P3T gives the maximum value, and as a result this A naught value is scaled up to the maximum level that is possible, and this noise then becomes negligible compared to this. So, this is sampled at T, capital T or multiples of capital T, because we want to amplify the signal part of the received signal part as much as possible. So, we are multiplying A naught by the maximum value by sampling at capital T, because this variance doesn't vary with sampling time. So, we have seen in this example why we sample at capital T when you use the matched filter as the receiver filter. We have seen that sampling at capital T gives you the maximum amplification of the noise part, and as a result it gives you the maximum SNR. If you sample at other places, the SNR will reduce. So, now we will also see in the next slides why matched filter itself is the best. Sampling at capital T is fine, but what should we use as a filter, that we will see later. But let us take another example of the matched filter. Suppose we have P1T is as this capital T, this is some level A. Now, again CT is taken as delta T, then P3T is the convolution of P1T, and P2T is P1T itself. So, P1 capital T, AT is P1 capital T minus T. We want convolution of this with P1T. So, let us write it in a different way. So, AT then P1 A tau then P1 T minus tau d tau. This is the convolution formula. So, this integration can be taken from appropriate 0 to T itself, because AT becomes 0 otherwise. So, this will become 0. So, we can take 0 to T itself, and then AT is P1 so P1 T and P1 small t minus tau d tau. So, A tau, the T will be replaced by tau. Okay. Now, this if we plot, we will see that this becomes again T 2T, it takes maximum value at T, is linear 2T T. It gives us maximum value at capital T. So, in both the examples we see that it is best to sample at capital T, because that gives us the maximum SNR by providing the maximum scaling to the signal part of the output signal. We take the output signal to the matched filter. If we sample it at capital T, we get the maximum scaling, and that gives us maximum SNR on the sampled value. So, now we will see why matched filter gives us the best SNR. Sampled at T, matched filter gives the best SNR. So, now let us take an arbitrary filter as a receive filter with impulse response AT. So, we have this RT. We will assume that we are transmitting again only one symbol P2T plus NT. So, because we are transmitting only, so this is not, so we will assume that we are using A0, we are just transmitting one symbol, 0th symbol, plus A2 NT, and then we are receiving that, passing through the match filter, and then sampling at capital T. So we will see what is the best filter to take to maximize the SNR here. Signal part here, the energy of signal part by the energy of noise part should be maximum. So what should be my AT, that we will see. So our RT is A naught P2T plus NT. Now we will assume that we are taking AK, this is the estimate of AK we want here. So we want to see what is the estimate. So what is AK? AK hat. So whether it is AK hat or some scaling of AK hat, I mean we do not know. So we will just sample at, this is YT, so this is YT, and we will evaluate YT. So this is actually the convolution of RT with AT at capital T. So A naught, then convolution of P2T and AT. So P2T and AT, so this part is the signal part. We will call it Y x of t. This is the signal part, plus this is the noise part, Y n of t. This is the signal part of this signal, and this is the noise part of this signal. We want to increase this. This is the desired part. We want to detect from here. This is of no use. This is only, it has noise. It does not have any contribution from A naught, whereas A naught actually carries the information. So this is undesired. This is desired. This is undesired. Undesired noise. So what is our SNR? See, from here, if we have only this, that is best, because that from there we can estimate the value of A naught t, because P2T we know already, it does not depend on A naught t, and AT also we know at the receiver. So we can compute this convolution beforehand and keep it computed, that is a constant, and just what we receive, we divide that by that constant, then we will get A naught exactly. But if there is some noise, that will corrupt the value and we will not be able to estimate A naught exactly. We will still divide the value by this part, but that will be A naught plus some noise, this part by this integration. So that will be some noise part. So how much the noise is compared to the signal part, that is of interest. That tells us how well we can estimate the symbol A naught. So let us compute the energy of this part and energy of this part. So SNR will be actually Yx t, the energy of Yxt, and the expected energy of Ynt, because this term actually is a random variable, because Nt is a random process, it is random. So the expected energy of the noise, and this is the signal part, energy of the signal part. So this is SNR. Now we just want to compute this and see what is the way to maximize this SNR. So what have we got? We want to compute first the expectation inside, the expectation of this noise part. This is, what is Ynt? It is the convolution. It is the convolution. So minus infinity to infinity, n star so Ynt, see mod Ynt, if you know this A is a complex variable, A plus IB, mod of this square is nothing but A plus IB, A minus IB. So this is the conjugate of this part. So you multiply this by the conjugate of this. So we are taking ynt conjugate and then ynt. We will evaluate 2 times, then multiply them. So ynt conjugate is the conjugate of the convolution. So conjugation will go inside. So yn tau a star t minus tau d tau. This is the conjugate of ynt. Yn star t is this, and then ynt itself is n tau a t minus tau d tau. This is this expectation. So we have taken the conjugate of this and then multiplied with this. So this we want to evaluate. We take it as a double integral, expectation. Now expectation of this integration will be a whole thing, this n star t, a star, n and a, all the things integral, but these two are not random. So these can come out of the expectation. So we take expectation of only these two, n star tau, n tau. Sorry, we don't want to take the same running variable here. So we take here t and here tau. So here you will have t and then a star t minus t, a t minus tau, dt d tau. So this expectation is not there anymore. Expectation is taken inside the integral. So now this we want to integrate. Now if you see this expectation, noise is assumed to be white. So there is no correlation between this different. So there is correlation only when t is equal to tau. So this is integral delta t minus tau a star t minus tau a t minus, this is a star t minus t, a t minus tau dt d tau. This is equal to, now this is n naught by 2, because noise is assumed to have, suppose n naught by 2 variance, that is the power spectral density, both two-sided power spectral density, then this expectation is delta t minus tau n naught by 2. At t equal to tau it is n naught by 2 delta, and at other places it is 0. So this at t equal to tau it is infinity, but other places it is 0. The variance is n naught by 2. So this part is non-zero only at t equal to tau. So only one integral will be there, say t, and delta t. So this will give us, because delta t minus tau integration with this will give us a star evaluated at t minus t. Then a t minus tau remains, t minus integration with this is this, and then this part remains. So we actually have a t minus t again dt. This is now this is the energy of this A. So we have not finished this proving matched filter is optimum in this class. That we will continue in the next class. So what we have done in that direction is that we are assuming that we are transmitting only one pulse, one symbol, A times P2 P1t, and then we are receiving A times P2t plus nt. Then we are passing that received signal through the filter and sampling at capital T. The output is sampled at capital T. We have seen that the output sample has two parts. One is signal part, one is noise part. If the noise part is not there, we can exactly estimate A naught t. But if the noise part is there, it will not give us exact estimate. It will have some noise. So we want to minimize that. So we want to maximize this scaling by this variance. So SNR is this yxt. This is the energy of this this by this one. We want to maximize the energy of this by the expected energy of this. So, towards that we are computing now this denominator, expectation of the noise part. So, we will continue doing it. I mean, we have computed this, and then we will argue later that matched filter actually gives us this best SNR here. So, in this class we have seen we have seen that using a matched filter we can demodulate a pulse amplitude modulated signal. We have then seen why we should sample whatever if we use matched filter, why should we sample at capital T. We have seen by we have seen two examples to really satisfy us that we should actually sample at capital T to maximize the SNR. That will give us the maximum SNR. So, and then we have started proving that matched filter is the optimum. We will continue and finish in the next class. Thank you. We will see you again in the next class.